Hello and welcome to this LPSolve demonstration. In this video, we'll walk through how to formulate a liquid milk blend using whole milk and milk replacer type ingredients to achieve a target solids and nutrient specifications at the lowest possible cost. Let's start by looking at the ingredient matrix. Ingredients are listed in the rows and nutrients are shown in the columns. In this example, we're using whole milk and water as the base ingredients, along with a 20/20 milk replacer as one possible option. We've also included several ingredients commonly used in calf milk replacers, such as dry fat, whey, skim milk powder, soy protein concentrate, WPC34, wheat gluten, and a small set of mineral and vitamin premixes. Our goal here is to allow LPSolve to choose between using a commercial milk replacer or building a blend from individual ingredients, depending on which option is least expensive while still meeting our specifications. Ingredient prices are entered in the cost per metric ton column, and we've set some reasonable minimum and maximums for several ingredients. For example, soy protein concentrate and wheat gluten are each limited to a maximum of 5% of the formula. We're also assuming if we use individual ingredients rather than a finished milk replacer, we'll include a calf milk replacer vitamin mineral premix. We'll begin by setting whole milk at a fixed amount of 50% of the blend, then allow LPSolve to formulate the remainder. The nutrient specifications are shown in the constraint rows. In this example, we want an average solids concentration of 15% with a maximum of 17%. Protein and fat both have defined minimums and maximums. Ash has an upper limit, and calcium, phosphorus, sodium, chloride, and magnesium are set as minimum requirements as defined in CAF Note 243 based on the 2020 NASM nutrient requirements for dairy cattle. With these constraints in place, we'll try to solve the formula. You'll notice that LPSolve reports an infeasible solution. This tells us that with whole milk restricted to a fixed amount of 50%, the available ingredients cannot meet all the nutrient specifications simultaneously. In other words, 50% whole milk simply isn't sufficient to reach these targets. To explore this further, we'll remove the minimum and maximum constraints on whole milk and rerun the model. This time, LPSolve finds a feasible solution, with whole milk entering at about 90% of the formula. In this solution, we meet our solids target between 15 and 17%, protein at 24%, fat near 28%, and all mineral constraints are satisfied. The resulting blend is approximately 90% whole milk, 6% water, about 1.4% wheat gluten, and a small amount of vitamin and minerals. Notably, none of the whey-based ingredients, skim milk powder, or the commercial milk replacer were used in this solution. The total formula cost is about $484 per metric ton. If we look at the shadow prices, we can see why some ingredients are excluded. For example, whey would need to be priced about $500 per metric ton to enter the formula, compared to its current price of roughly $900 per ton. Skim milk powder would need to be under about $860 per metric ton, far below its current price of about $3,000. Under these conditions, neither ingredient is economically competitive. To simplify the formulation, we can now fix whole milk at exactly 80% and rerun the model. This produces another feasible solution with a very similar result. Whole milk at 80%, water at about 14%, wheat gluten at 4%, and the remaining balance coming from minerals and premixes. The final blend contains about 15.2% solids, 24% protein, 25% fat, and meets all mineral specifications. You'll also notice a small amount of dicalcium phosphate, salt, and magnesium oxide entering the solution to satisfy calcium, sodium, and magnesium requirements respectively. Now let's see what happens if we restrict soy protein concentrate and wheat gluten to a maximum of only 0.1% each. When we do this, the model struggles to meet the 24% protein requirement using whole milk and milk-based ingredients. In fact, without higher protein ingredients such as SPC or WPC, the maximum protein concentration we can realistically achieve with whole milk is closer to 20 to 22%. We could confirm this by lowering the protein minimum and rerunning the model, but the conclusion is clear. Achieving higher protein levels requires additional protein sources. Well, this example highlights the strength of LPSolve. It allows us to evaluate trade-offs between whole milk and milk replacer ingredients, identify binding constraints, and understand which ingredients are economically and nutritionally necessary to meet our targets. Well, thanks for watching this demonstration, and be sure to check back for additional LPSolve training videos.